lecture 39. This is week 8 and we are talking about introduction to linear programming problems. In our previous lectures, we have introduced graphical solution of linear programming problem. Graphical solution of linear programming problems is convenient only when you have two variables. When you have more variables, the graphical solution is not a convenient method of solution. In the next week, we will talk about simplex method and its various adaptations. You will see that simplex methods can be used to solve linear programming problem of any variables. In this lecture and in the following lecture, we will lay some foundations for discussions on simplex methods that we will do in the next week. So, in this lecture, in particular, we will talk about how to express a linear programming problem in standard form. In general, a linear programming problem may be either a maximization problem or a minimization problem. It may include both equalities and inequalities as constants. It may have negative variables as well as positive variables. But we can convert any of these forms into one equivalent standard form, where the problem is always posed either as minimization or maximization problem, where all the constants either equalities or inequalities, and all the variables are positive. So, what we are basically saying is that in general, a linear programming problem may be a maximization problem or a minimization problem. It may include both equalities and inequalities as constants. It may have some positive variables, some negative variables, but it is always possible for us to convert an LPP of any of these forms to a standard form. And by standard form, I mean that the linear programming problem may be of minimization problem, all the constants may be of equality types, and all the variables will be positive. So, it is possible for us to convert any linear programming problem in this form, where the problem may be of minimization, all the constants will be of equality types, and all the decision variables will take non-negative values. So, we will see how to do that. So, the standard form of a linear programming problem with m constants and n variables, where n is greater than m, can be represented as shown. Note that the objective function is a linear function of the decision variables. So, either maximize or minimize, oftentimes we talk about minimization only. because we know the maximization then can be obtained by just taking negative sign of the problem. So, the objective function z equal to c 1 x 1 plus c 2 x 2 plus c 3 x 3 up to c n x n. The objective function is also known as cost functions. So, c 1, c 2, c 3, c n, they are all numbers associated with cost. Actually, you have seen the objective functions such as z equal to 600 x 1 plus 300 x 2. So, 600, 300 were the cost associated with the fertilizer problems. So, C 1 equal to 600, C 2 equal to 300, so on and so forth. So, the objective function is written as a linear function of decision variables. So, objective function is also known as cost function. Then all the constants are written as equations. A 1 1 x 1 plus A 1 2 x 2 up to A 1 n x n equal to B 1. So, you have n variables x 1, x 2 up to x n, and you have m constants. So, each constant corresponds to one equation. So, there are m rows of equations and n columns of variables. So, there are m rows of equations corresponding to m constants and there are n columns of variables corresponding to n variables. And A 1 1, A 1 2, A m n, all these things are coefficients. So, all these constants which are of equality type, the left hand side of these constants can be written as a matrix A x, where x represents the decision vector x 1, x 2 up to x n, and the matrix A represents a matrix of m rows, n columns, and the elements are the coefficients A 1 1, A 1 2 up to A 1 n, A 2 1, A 2 2, A 2 n, and finally A m 1, A m 2 up to A m n. B 1, B 2 up to B m represents the right hand side part of the constants. X 1 greater or equal to 0, x 2 greater or equal to 0 up to x n greater or equal to 0 represents non-negative variable constants, and B 1 greater or equal to 0, B 2 greater or equal to 0 up to B m greater or equal to 0 represents non-negative right hand side constants. So, in the standard form, we will express the right hand side of the constants as non-negative. So, we can represent these equations compactly using matrix notations. Note that using matrix notation, we can present the linear programming problem as maximize or minimize z equal to C transpose x. C is a vector n cross 1 vector, n vector, and x is also an n vector. So, z equal to C 1 x 1 plus C 2 x 2 up to C n x n will be valid when we take the C transpose and x 1 x. So, this is the C transpose vector and this is the x vector. So, the product will be C 1 x 1 plus C 2 x 2 up to C n x n. So, this is the objective function z equal to C transpose x. Subject to x equal to b, x is n vector, A is m cross n matrix, which comes from the left hand side part of the equality constants. All the constants has been written as equality constants, and b is the right hand side part of the constants, which will be written as non-negative. So, if any of these b's is negative, you have to multiply both sides by -1. So, that right hand side part becomes positive, and then you have these non-negativity statements x greater or equal to 0, b greater or equal to 0. So, A is m by n matrix, x is n vector, C is also n vector, and B is the right hand side part of the m equality constants. So, B is m vector. So, the matrix notation is again presented here more elaborately. Now, all linear programming problem will not come in standard form. Very often the constants are expressed as inequalities rather than equations. In some problems, not all the decision variables may be restricted to be non-negative. There are cases where some decision variables may be unrestricted in sign. That means, there is no sign restriction on the values of the variable. That means, that variable can take positive values as well as negative values, including 0. So, in other words, all linear programming problem will not come in standard form. So, the first step in solving a linear programming problem is to convert it to a problem in standard form, and in standard form we will express the linear programming problem, let us say as minimization problem or maybe maximization problem. We will have all the constants as equations, and the right hand side of all these equations will be non-negative. There will not be any variable which is unrestricted in sign, because we will have non-negativity constraint on all variables. So, the problem may be of minimization type, all the constants are equations, non-negativity constants on all the variables as well as the right hand side vector. Inequality constants can be converted to equations by introducing slack or surplus variables. Suppose I have a linear programming problem where I have inequality constants. The inequality constant may be less or equal to type or greater or equal to type. So, I have to convert this less or equal to type inequality constant or greater or equal to type inequality constant to equations, and that I can do by introducing slack or surplus variables. For example, let us consider this inequality constant 2x1 minus 5x2 plus 4x3 is less or equal to 8. So, the left hand side part is less or equal to 8. So, to make the left hand side equal to 8, I must add some non-negative value to the left hand side, so that it becomes equal to 8. So, I add S1 as a slack variable to the left hand side. So, my constant becomes 2x1 minus 5x2 plus 4x3 plus S1 equal to 8. So, S1 is the slack variable which when added to the left hand side part of the original inequality constant will be converted to an equality constant. The left hand side will be equal to 8. Similarly, if I have a constant of greater or equal to type, for example, 5x1 plus x2 plus 6x3 is greater or equal to 10. So, to make the left hand side equal to 10, I must subtract a part from the left hand side. So, I introduce a surplus variable S2 and rewrite the constant as 5x1 plus x2 plus 6x3 minus S2 equal to 10. Note that both S1 and S2 must be non-negative. So, S1 greater or equal to 0, S2 greater or equal to 0. So, by introducing two non-negative slack variable or surplus variable, it is possible for me to convert an inequality constant to an equality constant. When the inequality constant is less or equal to type, I have to introduce slack variable, and when the inequality constant is of greater or equal to type, I have to introduce surplus variable. Note that the slack variable is added and the surplus variable is subtracted. At optimal point, the values of these slack variable and surplus variables indicate whether the constraints are active, that means binding, or not. Remember that a constant is active when it is satisfied as 0. Now, how do I handle a decision variable that is unrestricted in sign? So, a decision variable which is unrestricted in sign is known as unrestricted variable. Sometimes decision variables are unrestricted in sign, that means they can take positive, negative or 0 values. In all such cases, the decision variables can be expressed as the difference between two new non-negative variables. Note that any variable that is unrestricted in sign can be expressed as difference of two non-negative variables. You can choose two non-negative variables appropriately such that their difference may be equal to 0, it may be less than 0 or it may be greater than 0. So, a variable which is unrestricted in sign, that means a unrestricted variable can be expressed as a difference of two non-negative variables. So, this is how I can handle unrestricted variables. For example, consider minimize z equal to x 1 minus 2 x 2 subject to x 2 greater or equal to 0, but x 1 is unrestricted. So, what I have to do is I first have to express x 1 as a difference of two non-negative new variables. So, I replace x 1 as x 3 minus x 4. So, I introduce two new non-negative variables x 3 and x 4 and replace x 1 as x 3 minus x 4. So, now my objective function z equal to x 1 minus x 2 becomes x 3 minus x 4 minus 2 x 2. And of course, the non-negativity constants now become x 2 greater or equal to 0, x 3 greater or equal to 0, x 4 greater or equal to 0. Note that the new problem formulation does not contain x 1, because x 1 has been replaced as difference of two new non-negative variables x 3 minus x 4. Let us now take an example of converting a given linear programming problem in standard form. Let us say the original problem is given as maximize x 1 plus 6 x 2, x 1 less or equal to 200, x 2 less or equal to 300, x 1 plus x 2 less or equal to 400 and x 1 x 2 greater or equal to 0. Let us say I want to express this linear programming problem in standard form, and let the standard form be minimization type. So, maximize x 1 plus 6 x 2 becomes minimize minus x 1 minus 6 x 2. X 1 is less or equal to 200. So, I have to introduce a slack variable x 1 plus s 1 equal to 200. Similarly, x 2 is less or equal to 300. I introduce slack variable s 2 and write x 2 plus s 2 equal to 300. X 1 plus x 2 less or equal to 400. Again, I have to introduce a slack variable and rewrite the constant as x 1 plus x 2 plus s 3 equal to 400. Then I will have non-negativity constant on x 1 and x 2 as well as s 1, s 2 and s 3. So, this is the standard form of the linear programming problem. We can also express these in matrix notation. So, my decision variable vector is x 1, x 2, s 1, s 2, s 3. The cost vector is minus 1, minus 6. The A matrix can be obtained and the B matrix is 200, 300 and 400. So, the problem formulation becomes minimization C transpose x subject to A x equal to B, x greater or equal to 0, B greater or equal to 0. Let us take another example. So, you want to write the linear programming problem in standard form. The problem is minimize z equal to x 1 minus 2 x 2 plus 3 x 3 subject to x 1 plus 2 x 2 plus x 3 less or equal to 9. So, it requires a slack variable. 2 x 1 plus 2 x 1 minus x 2 plus x 3 is greater or equal to 5. It requires surplus variable. 4 x 1 minus x 2 minus 2 x 3 equal to minus 6. So, this requires multiplication both sides by minus 1, so that the right hand side becomes positive. X 1 is greater or equal to 0, x 2 is greater or equal to 0, but x 3 is unrestricted. So, x 3 has to be replaced as a difference of two non-negative new variables. So, where is the solution? We first replace x 3 as x 4 minus x 5, introduce two new non-negative variables x 4 and x 5, introduce slack variables x 6, introduce surplus variable x 7. So, the objective function becomes x 1 minus 2 x 2, but 3 x 3 becomes 3 into x 3 minus x 4 minus x 5. So, 3 x 3 becomes 3 into x 4 minus x 5, because x 3 is replaced as x 4 minus x 5. So, the objective function becomes z equal to x 1 minus 2 x 2 plus 3 x 4 minus 3 x 5. Similarly, we have introduced the slack variable x 6 as well as x 3 has been replaced by x 4 minus x 5. Similarly, both the equations. In the first equation, we have introduced x 6 as surplus slack variables, and in the second equation, we have introduced x 7 as surplus variable. Finally, the last constant, we have multiplied both sides by minus 1, and then x 1, x 2, x 4, x 5, x 6, x 7 are all greater or equal to 0 because of non-negativity constants. So, this is how we can convert any linear programming problem which is given in non-standard form to standard form. So, let us revisit the fertilizer problem. So, let us go to the problem as formulated. Minimize z equal to 600 x 1 plus 300 x 2, 2 x 1 plus 4 x 2 is greater or equal to 16, 4 x 1 plus 3 x 2 is greater or equal to 24, and x 1 greater or equal to 0, x 2 greater or equal to 0. We have solved this problem, and we have seen that corner point A is the optimal solution. The objective function value is minimum at point A. Now, let us introduce slack variables or surplus variables, whichever is required, to convert these inequality constants to equality constants. By doing that, we will now see how do we transit from graphical solution to algebraic solution. This fertilizer problem we have solved in our previous lecture using graphical method. It is a problem with two variables and can be very conveniently solved by graphical method. When you have many variables, the graphical method is not a convenient way of solving linear programming problem, and the simplex method, which is basically an algebraic method, must be used. So, let us take this simple example and let us see how this transition is possible from graphical solution to algebraic solution. So, this fertilizer problem has two greater or equal to type constants. So, I have to introduce surplus variables S 1 and S 2, and after introducing these two surplus variables, my constants are 2 x 1 plus 4 x 2 minus S 1 equal to 16 and 4 x 1 plus 3 x 2 minus S 2 equal to 24. Note that x 1, x 2, S 1, S 2 are all non-negative. Also note that when you introduce slack variables or surplus variables, they do not contribute to cost function. So, the cost in the cost function, the slack variables or surplus variables do not appear. That is why I have multiplied S 1 and S 2 by 0 there. Now, we have these 4 variables now, x 1, x 2, S 1 and S 2, and I want to consider algebraic solution. The solution space has 2 equations and 4 variables. Then how do I find the corner points? The corner points can be found by setting 2 variables to 0 and solving for the remaining 2 variables. You have 2 variables, you have 4 variables and 2 equations. You have 4 variables and 2 equations. So, you can set 2 variables to 0 and can solve for the remaining 2 variables. And by doing this, we can find all the corner points. So, there are 6 combinations possible. You can set both S 1 and S 2 equal to 0. You can set both x 1 and x 2 equal to 0. You can set x 1 equal to 0, S 1 equal to 0, x 1 equal to 0, S 2 equal to 0, and x 2 equal to 0, S 1 equal to 0, x 2 equal to 0, S 2 equal to 0. So, all these 6 cases possible, and when you do this, you can easily find out the optimal solution algebraically, because in that case you will have 2 variables, 2 equations. So, you can completely solve. For example, if I set S 1 equal to 0 and S 2 equal to 0 in these 2 equations, I have 2 x 1 plus 4 x 2 equal to 16 and 4 x 1 plus 3 x 2 equal to 24. 2 equations, 2 variables, I can easily solve to get x 1 equal to 4.8, x 2 equal to 1.6. The question I ask is now, is this solution feasible? That means, does this solution satisfy all the constants? Yes, it does, because x 1, x 2 are all greater than 0. Similarly, S 1, S 2 both are 0. So, they satisfy S 1 greater or equal to 0, S 2 greater or equal to 0. So, solution is feasible. In fact, this is the optimal solution as we have seen in previous lecture. Similarly, if I set x 1 equal to 0 and x 2 equal to 0, the solution is straightforward, S 1 equal to minus 16 and S 2 equal to minus 24. The solution is not feasible now, because both S 1 and S 2 must be greater or equal to 0. Similarly, you can set x 1 equal to 0 S1 equal to 0 and can obtain x2 equal to 4, S2 equal to minus 12. Again it is not feasible because S2 is negative. You can set x1 equal to 0 and S2 equal to 0 and we will obtain x2 equal to 8, S1 equal to 16. It is a feasible solution. You can set x2 equal to 0 and S1 equal to 0, you get x1 equal to 8, S2 equal to 8. Once again it is a feasible solution because all the constraints are satisfied. x2 equal to 0, S2 equal to 0 will give you solution as x1 equal to 6, x1 equal to minus 4. Now, this is not feasible because S1 cannot have negative value. So, it is possible for me to solve algebraically these set of equations where I have two equations, 4 variables by setting 2 variables to 0 and solving the remaining. And I have 6 scenarios and I find that 3 solutions are feasible, 3 solutions are not. So, now look at that graphical solution that we have seen in your previous lecture. Let us locate all these 6 points. S1 equal to 0, S2 equal to 0. This is point B, which is a feasible solution with objective function value 3360. X1 equal to 0, X2 equal to 0, this is the origin and it is not feasible. X1 equal to 0, S1 equal to 0, the solution is x2 equal to 4 and S2 equal to minus 12. This is point E, this is not feasible. Also look at graphically that this is outside the feasible region. Similarly, x1 equal to 0, S2 equal to 0, the solution is x2 equal to 8, S1 equal to 16 and this is the corner point A. It is feasible and has 2400 as objective function value. In fact, this is the optimal solution. Then x2 equal to 0, S1 equal to 0, the solution is x1 equal to 8, S2 equal to 8 and this is point C, which lies within the feasible region. It is a feasible solution with objective function value 4800. Finally, S2 equal to 0, S2 equal to 0, x1 equal to 6 and S1 equal to minus 4 as the solution. This corresponds to point F. This is not feasible because it is lying outside the feasible region. Note that point E, point F and the origin are outside the shaded region. Shaded region represents feasible region here. We get all these informations from the algebraic solution as well. Optimum solution is located at point A as usual and whatever conclusion we have drawn using graphical method of solution, we draw the same conclusion using algebraic solution. The algebraic solution is obtained for 4 variable 2 equation system by taking 2 variables equal to 0 and remaining for the other 2 variables. These equivalence between this graphical solution and algebraic solution leads to the simplex method that we will discuss in our previous week's lecture. With this, we stop our discussion on lecture 39 here.